So thank you everyone for coming to QMat Cafe. This is an initiative of some QMat fellows, Sayedli, Chevati. Denis Jankovic also helped us to set up this. So this is a serious online talk that it's going to be focusing different aspects of QMat community. So we will have some ultra cold atoms as today, quantum information as well, also high energy physics. And also we are going to invite some industry partners to talk about the opportunities in the industry and other topics related. So today we have Denis Jankovic, who is a local student from the University of Strasbourg. He did his Master 1 and now he's doing the Master 2 of condensed matter and nanophysics, and he's one of the QMat fellows. And he's going to present about nuclear spins in single molecules, magnets, and qudits, case of study of PCTB. And also we have a guest speaker, Sergio Cantu, who come from US, if I understand. You were raised in Mexico. You did your undergrad in the University of Texas in Brownsville in physics and mathematics, and then you went to the summer research program of MIT, where helped you to get into a PhD in MIT under the supervision of Professor Vladan Voletic in the Center of Ultra Cold Atom. So I think we have a very good speakers today. We will start with Denis, and if you have any questions, please write it in the chat. Maybe we can make all of them at the end. So I will stop sharing here. Please give a welcome to the speaker. Okay. Stop sharing.
So does everybody see me? Hello? Or my screen too? Nice. So if everybody sees my screen, I can start. So I will talk to you today about my internship I'm doing this year. So under the supervision of Paul-Antoine Hervieux at the IPCMS and Mario Ruben at the IPCMS and KIT. So it will be about, nuclear spins as qudits in single molecule magnets, and especially in TB PC2 or PC2 TB. So I'm very happy to be here today to be the first official talk from QMat Cafe. So I will try by introducing the subject. So a quick recap on quantum information. I guess all of you know more or less what it is, but so we have classical bits that everybody knows about. So you can have a bit that can be either in a 0 or 1 state. It's a 2-level system. And when you have n bits, you can have n to the power of n different combinations. Well, with qubits, it's the same, but it's a quantum physical 2-level system. So you can be in the superposition of 0 and the superposition of 1 and superposition of both. And with n qubits, you can have to the power of n coefficients. This means that you can work in a superposition of all of them and then work with all of those coefficients at the same time during your calculations. This is why people say when you have n qubits, you actually have 2 to the power of n classical bits equivalents. Now, something maybe some of you don't know about is qudits with a D. So qubit is a 2-level quantum physical system. A qudit is a D-level quantum physical system. And in our case, D is equal to 4. So this means that you can have be in a superposition of 4 different states, 0, 1, 2, 3. And especially with n different qudits, we can be in a superposition of D to the power of n different combinations. So with only D equal 4, you need 2 times less physical systems for the same quantity of information as a qubit. So that's a nice improvement. And here, the qudit we are talking about is this kind of big molecule here that's called the Bisphthalocyanine terbium. So it's a tongue twister. People just call it TBPC2 or PC2TB or terbium double decker. So it's a big molecule that was originally used as a single molecule magnet. And you can see in the middle, there is a central atom here. That's actually an ion. It's a Terbium III ion. And well, its ground state can be calculated and is the xenon 4f8 ground state. So this means that it has a core electron state as xenon and then 8 electrons in the 4f shell. And also, in accordance to Hund's rule, if you calculate the ground state, you can see that the ground state is the spectroscopic symbol term 7f6. This means that the total spin of all the electrons is 3, the total orbital angular momentum is 3, and the total angular momentum is 6. But what's interesting here, and this is why we are talking about a qudit, it's because the terbium nucleus has a spin of 3 halves. So it can be in a superposition of 3 half, 1 half, minus 1 half, or minus 3 half. And this is our Q for it here. So what my internship is all about is trying to theoretically recalculate the electronic energy levels and to try to simulate all the parameters that we can change in the physical system so we can, engineer these electronic levels. I'm talking about electronic levels, even though our system is the nucleus, because the nucleus is very small and it's very hard to interact directly with it. You can see that the nucleus is 10,000 times at a 10,000 times smaller scale than the electrons. But we know how to interact with the electrons easily, and the electrons are interacting with the nucleus thanks to what's called the hyperfine interaction. And so any energy state or any state of the nucleus can be seen in the energy spectrum of the electrons. And so to modelize the electronic energy levels, we need to start from the free ion, so without any molecule. So the ion is subjected to 2 main Hamiltonians. I mean, the first Hamiltonian is the electronic structure, so just the electrons orbiting independently around a certain nuclear distribution, charge distribution. And then we have the interelectronic repulsion between all the electrons. That's a simply Coulombic repulsion. But we can, for computational purposes, we can do it better. We can have a central field. So electronic structure Hamiltonian is simply the monopole effect of a central point charge of the nucleus. And then you add the mean field contribution of all the interelectronic repulsion, and you plug all of this in something that's called the mean field potential, U. And then you have a central field Hamiltonian. And this can be used as a main Hamiltonian, and then add the residual electron repulsion as a perturbation. And so when you do this, you have already the electronic spectrum that's starting to appear here. So we first have splittings between different electronic structure levels. So depending where the electron is, as I said, the ground state is 8 electrons in the 4f shell, but we can consider 1 electron that went excited and went up there. And the separation here is about 10 electron volts already, so it's pretty big. But then if we add the residual Coulombic interaction, we see that the interelectronic repulsion adds another splitting of 10 times smaller, so of 1 electron volts, between the different L and S states. But then we can go a bit further because another interaction that's happening inside the atom is the spin-orbit coupling between the electrons between themselves. So here we're in the case that's considered the LS coupling. So we consider the total orbital angular momentum that's interacting with the total spin angular momentum of all the electrons. And this takes this simple form with lambda, the coupling constant. And if you want to calculate it, we need to go from the non-coupled basis L, ML, S, MS to the coupled basis, so LS, J, MJ, where J is the total angular momentum. And so here again, there is another splitting appearing, so 10 times smaller again, so 0.1 electron volts. So this splitting now differentiates the states with different total angular momentum J. And as we can see, the ground state is J equals 6. So now we can consider what's happening if you put this atom inside the molecule. So it's subjected to this beast here, the Ligand-field Hamiltonian. So it's quite complicated mathematically, but it's just a multiple expansion of the electrostatic repulsion of the electronic charge inside the molecule on the atom. And it can be very much simplified. The different coefficients equal to 0 depending on the geometry of the molecule. So here the different coefficients are the geometrical coordination factor that depends on the electronic charge distribution inside the ligand, and the Stevens operator that will be the one that we only take a finite value, a non-zero value, depending on the geometry of the molecule. So in our case, it takes this geometry here with only 5 coefficients, and one of them is even equal to 0 again, so only 4 coefficients. So those ones can be obtained from experimental results or from ab initio DFT calculations. And using this, we can plug this again inside our Hamiltonian, and we can have another splitting appearing, but now between states of different J projections. So now MJ can be equal to plus or minus 6, plus or minus 5, etc., until we get to 0. And here the splitting is of 0.01 electron volts. Thermally, it corresponds to approximately 400 kelvins. So this means that if you are cold enough, and very cold, because so this is based on an experiment they're doing in Karlsruhe. They are very cold in a almost 0K temperature. And here we can consider that the whole system is in the ground state, so J equals 6, MJ equals plus or minus 6, as a first approximation. So now we can finally go to the core of the subject without any puns, but we are talking about the nucleus. So the nucleus is not a point charge. And so it has first a magnetic dipole. This magnetic dipole creates a vector potential. And the magnetic dipole is directly proportional to the nuclear spin operator, with the gyromagnetic ratio and the nuclear magneton being the proportional coefficients. So for the terbium, as I said before, I is equal to 3/2. So the projection can take 4 different values. And here A, so this vector potential, if we consider that we are in only one J substate, that's the case here. As we said, you can consider that we are in only one J substate. Takes this effective form if we have an electron submitted to this vector potential. It is under the effect of this effective Hamiltonian here. That's again just a coupling Hamiltonian between the nuclear spin and the total angular momentum of the electrons. And the dipole hyperfine coupling is very small, as you can see, 10 to the power minus 5 electron volts. So it's a very small effect. So we can work in 2 bases again, but since it's a small effect, we can work in the non-coupled basis and to the first order in energy. So the non-coupled basis, in this basis, the first order perturbation of the magnetic dipole interaction takes this form. So this means that each MJ state will be divided in 2 to the power of I plus 1 substates, and with a constant spacing of A times MJ. What this means for the terbium atom here is that we will have for MJ equals plus or minus 6, as we said before, the ground state is MJ equals plus or minus 6. It will be divided in 4 different levels, all separated by the same energy spacing here. However, now that's not good enough if we want to have a Qudit, because a Qudit access each transition between each nuclear state individually. But here we cannot do that since they are all spaced equally. So we need something else. But thankfully, as I said before, we are looking at the charge distribution of the nucleus. So there will also be an electric quadrupole appearing from the nucleus. So it will create a certain electric potential with a nuclear electric quadrupole. So again, it's just a multipolar expression. But when we submit an electron with a constant J substate as before to this electric field, you obtain this effective Hamiltonian for the electrons. And so B here is again the quadrupole hyperfine coupling constant, and it is at the same order of magnitude as A for this case. And so here MJ is equal to plus or minus 6, And when you calculate the first order energy perturbation for the non-coupled basis, we get something like this. So as we can see now, it's not linear in MA as we had before. So the spacing here will not be constant anymore. They will each have their certain value, bigger and bigger according to, MA. And this is nice because now we can address each energy level spacing individually. And with this, you can do very nice things because you can, for example, implement what's called the Grover's algorithm. So Grover's algorithm is a quantum algorithm that speeds up database aging or function inversion. So simply, it allows to look inside a list of values very rapidly. Because for our n-element database, you will be of complexity linear to the number of elements with a classical algorithm at best. But with a quantum algorithm here, the Grover's one, you will be at a square root of n complexity. So the increase in speed is quite nice, especially for big databases. So this here you can see here is a quantum circuit with quantum gates, but for example 3 qubits. So it's very complicated, but what you can see is that each quantum gate is actually a matrix that acts on the different qubits. And so we can have the same thing here for the Qudit, because as I said before, each energy spacing can be addressed separately, so that we can, if we shine, for example, a microwave pulse on the or an optical pulse on the atom, we can trigger each hyperfine transition here from the ground state, and with, for example, 3 different wavelengths and 3 different dephasing, so delta, we can have a very specific, let's say, evolution Hamiltonian here in the rotating wave approximation. And so this means that we can, this HQD can take any form we want him to be, especially to create these H and X quantum gates we saw before. And so we can start with initializing the system in a certain nuclear state. Then we applied the H matrix we saw before, and it creates a superposition of all configurations. And then we can apply a pulse again that takes the different forms of the Hamiltonian of the matrices to have the good quantum gates to get the Grover algorithm working, and only select one specific superposition. And then when we simply read the system out, we get the only level we want it to be. So this was done in Karlsruhe by the team of Wolfgang Wernsdorfer and Mario Ruben. So now what's next, and what's next for my internship too, because I did manage to do this, to resimulate this model. But now we can look at what's happening when you apply an electric field on the molecule. That's what's called the Stark effect. Because what's been demonstrated experimentally, but was not exactly explained theoretically, is that when you apply an electric field, obviously the electronic wave function changes. And this change in the electronic wave function will change the hyperfine coupling constant A and B, since those two coupling constants depend on the wave function. And so you can couple and decouple the nucleus and the electron at will, because the main problem with all qubits and qudits is that you want them to be the most decoupled from the environment as possible, so that they can stay coherent the longest, but you also want them to couple them to the environment nonetheless, because you want to measure them. So here, maybe by applying an electric field, you can try to see and try to couple and decouple this nucleus from the electrons, so that when you don't measure it, you decouple it, and when you want to measure it, you apply another electric field that that couples the nucleus to the electron, so you can measure it very very fast. Another thing that can be seen is that here I had one double decker, but we can have triple deckers, 4 quadruple deckers, pentuple deckers, and all of them we then we can then entangle all of these qudits for 4 levels, or even more than 4 levels if you take another atom than terbium. For example, for this prosium, you can even take 6 different levels. And then you can all couple them, and you can have a big Hilbert space. So only by creating this quadruple decker, quintuple decker, you can have big possibilities of d to the power of n states that you can calculate with. And this makes use of what's called the Erkakaya interaction, because this nuclear spin will be coupled together through the electronic spins of the molecule. So it's a truly multidisciplinary project, because we will need quantum chemists to study how the ligand or the molecule interacts with the electric field, nuclear physicists, because we need to model the charge and current distribution inside the nucleus, so we can get the better values for the magnetic dipole and the electric quadrupole. Computer scientists and mathematicians, because we are working with qudits and not qubits, and the qudit algorithmic is really not developed yet. So maybe we can see some things where qudits can be used more efficiently than qubits for some calculations, etc. So I want to thank you, and I'm really sorry if I exceeded the time, because my timer didn't work this time, so I wasn't able to see it. But so if you have any question, I'm open to it. So I don't know if anybody else can hear me.
So yeah. Thank you very much, Denis. I'm going to mute you, and then we can thanks to Denis. So if anyone have questions.
I have a question, if that's okay.
Yeah.
Then it's thank you for your talk. That was a very interesting talk. It's not very often that I see Hunt's rule used in talks, so that was nice. Do you see any, like, what advantages do you see if one were to use different isotopes to get different qubits? Like, you know, do you see kind of like a
very good question, because that's what they. So well, let me just share my screen again. So do you see my screen?
Yes.
Yes. Okay, because that's what they studied in Karlsruhe, actually. That's what they call isotopal chemistry. So if you change the isotope, so for the terbium, it's not really durable, because terbium has only one really stable isotope. But they did it for dysprosium, for example. And when you change the isotope of the nucleus, I mean, if you change the nucleus, you will change the nuclear spin. So, for example, it won't be I equal 3/2 anymore. It will be I equal 5/2, for example. But you also change the magnetic dipole, and you will also change the quadrupole. So you will change those spacings here. So you can change it to have the best different kind of spacings you want. For example, if you want to have them to be very different one from another, you can maybe try some different isotopes until you get the best parameters for the best energy spacing difference here. If I was clear enough, and audible too, because.
Yeah.
Okay.
Thank you.
Thank you.
Denis, one question.
Yes.
You said that this has been done experimentally here in IPCMS?
No, in Karlsruhe.
Okay. Okay.
Yeah. So what I'm doing here is I'm trying to find, well, to recalculate mathematically all the Hamiltonian elements, and to do numerical simulations with to get this spectrum, so we can try, because it's experimentally very expensive to try all different elements and all of different isotopes. So maybe with a code we can try different types, so we can tell them this is the most ideal kind of atom you want to use in your experiment.
Okay. Okay. Mm-hmm.
And so we're also working with nuclear physicists at the IPHC, especially for this isotope thing that Sergio was talking about.
Yeah.
I have a question, Denis.
Yes.
So would you mind to a little bit draft how would be a quantum gate for a qubit? Because we know for qubits the Pauli operations works pretty fine. But how looks a matrix for a qudit?
Well, for example, I mean, you just increase the how do you call it? You just increase the dimension of the matrix. So maybe I will just try something fun here. So do you see a whiteboard?
Yeah.
Yeah. So basically, when you have two qubits that are entering a quantum gate and then exiting, the quantum gate is a 4x4. So it will be something. I won't do it, but it will be a 4x4 matrix. And so here you will have this submatrix here that will be for the first qubit. This submatrix here will be for the second qubit, and the submatrices here will be for the entanglements and all the calculations with both qubits. I mean, if they're interacting. But with a qudit, for example, a Q4 well, it will be the same, but the submatrices will be 4x4. So you will have a 16 by a 8 by 8. Sorry. We'll have a 8 by 8 matrix here. So 8 by 8 still will be a 4x4, 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 and 4x4.
And this also implies that your basis set that span your space, it have to be larger, right?
Yes, exactly. And that's the kind of good thing we get with qudits, is that you only have one physical system, but we have a larger ensemble of states. But the only drawback here is that only when you have one qudit that has a dimension 4, well, you can. It's not exactly equivalent to 2 qubits, because what's happening here is that you cannot entangle the qudit with itself, while with 2 qubits you can entangle the 2 qubits with themselves. That's what they call. There was some terms for that, for this entanglement, to quantify this entanglement density. So qudits can be more dense with information physically, but less dense when it's about entanglement.
And the complexity of these quantum gates also increase the complexity of the quantum algorithm you want to do? I mean, experimentally, because experimentally, I guess it's more complicated or not.
So when you say complexity, you are not talking about the big O notation that you see in computer science.
Because I know I'm talking about the sequence of pulses you're talking about before.
Absolutely. Because if you have 2 Q for it, then you have you need to have 2 different multi-wave. For example, if you have a qubit, you then just have one laser with only one wavelength. That's figure it, and you have 2 qubits when it's 2 lasers. Well, here, if you have 4 levels, you will need 1, 2, 3 different wavelengths. And so if you have 2 Q for it, then you will need 6 different lasers, etc.
Okay. Good. Thanks. I don't see if there is any other question in the chat.
I don't see any question on YouTube either, but like there are 4 people on YouTube, so
okay,
that's that.
I just have one question.
Yes.
Do you consider your central atom as free, interacting with the path of the Ligand-field, or do you, if you try to make a simulation, is it possible to modelize the interaction of your terbium atom with all the atomic molecules? What is a simpler way to get kind of
what's happening here?
What is the simple way to get the performing simulation to make some quantum calculations?
So what's happening here is that the molecule is treated as a perturbation because the 4f electrons are well shielded from the environment. And so the only non-perturbative Hamiltonian is the central field one. And so you can treat the ligand or the molecule as a perturbation on it. And this is how the interaction with the molecule is done. But what is that it's not exact. And if you take, if you go either further than what's called the Ligand-field theory, and you take correlations on interelectronic configurations correlations. So when you have correlations between the 4F7 and 5D1 and 4F8 5D0 states, so you can have some correlations between those two states, and you take this into account. Then for the 5D electrons, the Ligand field is really interacting with it, and again, literally from a condensed matter point of view, well, exchange electrons with it. Like the 5D electron is almost like inside the ligand. So in this case, when you take this into account, and this is very important for the Stark effect, because this one is a node parity one state. So the Stark effect, linear Stark effect will appear when you take this one into account. This is very important. And then you need to do some kind of mixing between atomic physics models and DFT models to try to see how all of this is interacting. I don't know if I answered your question, but.
Okay. To make the link with my own internship, is it possible to imagine an experimental lattice with each side fulfilled with one of your molecule, and make some very large spin structures using your to make some calculation at 2 scales?
I mean, theoretically, it needs to be very careful about is the geometry of the crystal or the molecule around the central atom, because this will directly affect how you have mixings between different J projection states, because this molecule here has a very nice symmetry, and this makes it that the different total angular momentum projection are very separate one from another. While if you take another symmetry of crystal, then the MJ will mix together, and you won't be able to use it for quantum information processing anymore. So it should be theoretically possible, but then you need to also keep in mind that the geometry of the crystal is very important. So you cannot just, you need to find a good crystal to put the terbium atom into, so as to not lead to degeneracies. So that's I mean, the new degeneracies are not very too much different from the 3-ion ones.
Okay. Thank you.
No problem.
So I think if there is no more questions, we can move to Sergio Cantu's presentation. And thanks to Denis again.
Thank you for organizing all of this.